Unlike other routing protocols, OSPF routers do not share routing information with all connected routers. They first build a neighborship and then share routing information only with neighbors. The entire process goes through the 7 states. They use the first 3 states to build a neighborship. If a neighborship forms, they use the remaining 4 states to exchange routing information. Let us understand these states in detail. In the down state, a router knows nothing about its neighbors. An OSPF process always starts in this state. In this state, it first selects a unique router ID. Routers use it to identify each other. It is a 32-bit numeric ID. It has the same format as an IP address uses in decimal notation. After selecting the router ID, it sends hello packets from all active interfaces and waits for a response from other OSPF routers. A hello packet includes all the parameters that other OSPF routers need to determine whether they will form a neighborship with the sender router. It uses OSPF multicast address 224.0.0.5 to send hello packets. It sends hello packets at a regular interval. The interval is called the hello interval. It also listens to this address to receive hello packets from other OSPF routers. A router enters the init state when it receives a hello from a router that is not in its neighbor table. It compares the hello packet's parameters with the locally configured. If both match, it adds the sender router's router ID to its neighbor table and prepares the reply. A router enters the two-way state when it receives a reply from a router that is not in its neighbor list. This message informs the hello sender router that its parameters match the hello receiver router's parameters, and the hello receiver router is ready to become a neighbor. If this router is willing to build a neighborship, it can reply with another hello packet. If the router replies, both routers enter the two-way state. If 2 routers reach this state, it means that both routers have met all OSPF configuration requirements to become neighbors. At this point, they are neighbors and ready to exchange their routing information. They use the remaining steps to exchange the routing information. Before we discuss them, let us understand the parameters routers match to become neighbors. Routers match the 5 parameters to establish neighborship. These parameters are area ID, hello and dead interval timers, authentication, stub flag, and MTU. OSPF uses areas to scale and optimize networks. OSPF areas serve as logical boundaries for routing information. By default, routers do not share routing information beyond their respective OSPF areas. 2 routers become neighbors only if they are in the same area. An area covers only the router's interface, not the entire router. You can configure a single router to operate in multiple OSPF areas. For example, a router with a serial interface and a fast Ethernet interface can run the serial interface in one area and the fast Ethernet in another. To ensure that 2 routers are in the same area, the link connecting them must be in the same area, including the interfaces at both ends. In this network, R1, R2, and R3 belong to the same OSPF area. They will check the remaining parameters to build a neighborship. Similarly, R4, R5, and R6 belong to the same OSPF area. They will also check the remaining parameters to build a neighborship. The network ID is not a requirement for the OSPF neighborship. However, it directly affects the process of becoming a neighbor. A link comes up only when both end interfaces have an IP address from the same subnet. If both end interfaces have IP configurations from different IP subnets, they cannot exchange IP packets. OSPF uses IP packets to share information between interfaces. If 2 interfaces cannot exchange IP packets, they cannot build an OSPF neighborship. In this example, R2 and R3 belong to the same OSPF area. However, they cannot become neighbors. The link that connects them has an IP configuration from different subnets. R2 serial 0/0/0 interface has an IP address from the subnet 192.168.0.0/30, while R3 serial 0/0/0 interface has an IP address from the subnet 192.168.0.4/30. To fix this issue, you must change the IP address of any of these interfaces. You can either change this IP address to 192.168.0.6/30 or this IP address to 192.168.0.2/30. After that, this link will come up. To enhance network security, OSPF allows you to configure the password for specific areas. Routers that have the same password will be eligible for neighborship. To use this facility, you must configure the password on all routers you want to include in the password-secured network. If you skip a router, the router will not join this network. When routers see each other's hello packets in the segment, they try to match all neighborship configuration values, including the password field. If the value of this field does not match, routers will ignore each other's packets. An OSPF router uses hello packets to discover and establish neighborship with other OSPF routers in the network. It sends hello packets at a specific interval. This interval is known as the hello interval. After building the neighborship, it uses hello packets to maintain the neighborship. The default hello interval is 10 seconds. It accepts a hello packet from the neighbor every 10 seconds. If it does not receive a hello packet in a hello interval, it waits for a specific period. This period is known as the dead interval. After the dead interval, it removes the router from the neighbor list. The default dead interval is 40 seconds. Two routers will become neighbors only when their hello and dead intervals match. OSPF supports various types of areas to optimize the network, improve performance, and reduce the amount of routing information that routers exchange. A stub area is a special type of area. OSPF does not flood external networks in the stub areas. Routing from stub areas to the outside world is based on a default route. Stub area configuration reduces the size of the topology database and the memory requirements. A stub area has a single exit point. Two routers will become neighbors only when their stub area flags match. MTU is the maximum size of a data packet the interface can transport. Different interfaces can have different MTUs. It is an optional value. Routers can become neighbors even if their MTU values do not match. However, they will not be able to exchange routing updates. For an error-free OSPF network, you must maintain this value consistently across all routers. After becoming neighbors, how routers exchange routing information depends on the network topology. If it is a point-to-point network, they immediately enter the Exstrat State to start the exchange process. If it is an Ethernet broadcast network, they first elect a DR and a BDR, then enter. A BDR is a hot standby for DR. If DR fails, it immediately becomes DR. Apart from the DR and BDR, all other routers in the segment are DRO others. DRO others exchange routing information only with DR. They do not share routing information directly. A DRO other talks to a DR using the multicast address 224.0.0.6. DR and the BDR talk to DRO others using the 224.0.0.5 multicast address. After finalizing their roles, routers enter the Exstrat state. In this state, routers build adjacency. Adjacency allows directly connected routers to exchange routing information. In an Ethernet broadcast segment, DR builds adjacency with each DRO other. Each adjacency contains two adjacent routers. The router with the highest router ID becomes the master and starts the exchange process by sharing its routing information. The remaining router becomes the slave and receives the routing update from the master in the exchange state. The master starts the exchange process. Routers exchange routing information using LSAs. An LSA is a small portion of a database. It contains information only about a specific link. All routers maintain a database of LSAs. In the exchange state, they share a list of LSAs in their databases. Each LSA has a unique ID. Routers use it to check which LSAs they already have and then request only the LSAs they do not have from the other router. Let us take an example. The master sends a list of LSAs from its database to the slave. The list contains information about 10 LSAs. The slave checks its database and finds 4 of those LSAs. Therefore, it will only request 6 LSAs using a link state request packet. Similarly, the master compares the list it receives from the slave and requests the LSAs it does not have in its database. At the end of this state, all routers in the adjacency know which LSAs they have in their database and have requested the LSAs they do not. In the loading state, the master and slave provide the requested LSAs and incorporate the received LSAs into their respective databases. Then, they send an acknowledgement LSA to update each other. Once the master and the slave are synchronized, you can consider them to be in a full state. That's all for this video. In this video, I explained how OSPF routers establish neighborship and exchange routing information. If you have any comments, suggestions, or feedback, please share them in the comments section.